So we left off here with what problem was this? This was number 4, example number 4. We just got a few more examples to work our way through. The first one here is going to be example 5. This is a classic calculus problem. We're trying to get from point A to point B, and we have to pass through an area that's slow, and then another area that's fast. So I am 1 mile from the ocean. That's this distance right here. And wish to get to town 3 miles down the shore. And this shoreline's very rocky, apparently. I need to swim to the shore. So this is me swimming down here. And then walk to the shore. If I want to minimize my time, not necessarily my distance, because the shortest distance between 2 points is going to be a diagonal line. But the hard thing about that is that'd be all swimming. That'd be all slow. I need to do a combination of some slow and some fast. Because the diagonal slow is actually short distance, but it's going slow. So what we're looking at then is if I swim at 2 miles per hour, walk at 4 miles per hour, I need to consider how do I relate that with distances and rates and times. Wait a second, we have an equation. I like to call it the dirt equation. D equals RT, which also means that D over R equals T, or D over T equals R. Now it's asking us to minimize our time. So let's color code some of this stuff. We'll color code the blue in blue because it's in the water. We'll call that our first time. So our time here, time 1, is going to be the first distance divided by the first rate. Then our time 2, which is going to be here on the land, is going to be the second distance divided by the second rate. So let's figure out what we got going on. The first thing I notice is this x, and because that x is there, that gives me a way to calculate each of these two distances. The red distance is going to be 12 minus x. So we know that the second distance is equal to 12 minus x. But if we were to divide that by the second rate, which is 4, that's going to be our second time. All right, let's look at the first distance now. We know we got x and 1, and then if you're trying to figure out the hypotenuse or a diagonal distance, we know that x squared plus 1 squared equals that d1 squared. So if I square root both sides, then I get that distance for the swimming is the square root of x squared plus 1, because 1 squared is 1. So the first distance is equal to the square root of x squared plus 1. And if I divide that by the first rate, which in this case is 2, that gives me the first time. So then what I want to do is combine the red and blue, make some purple here, and find a total time. Time total. That's going to be our time 1 plus our time 2, which in this case is square root of x squared plus 1 over 2, plus 12 minus x over 4. Let's call this t of x, or t of x. What we want to do is then find t prime of x, set it equal to 0, and then solve. Okay, now this has a lot going on in here, and this is mostly dealing with derivatives. And right now I help you set it up, but I want to show you how you can use your calculator to calculate this, essentially. So we're going to go to our calculator. I'm going to go to the y equals. Now I have two different times, so I'm actually going to keep them separate. You don't have to do it this way, but this is kind of my preference here. So the first time, our time 1, is going to be a square root over 2, so we're going to have second square root of x squared plus 1, and we divide that by 2. Then our second one is going to be 12 minus x on top, and we divide that by 4. If we add those two together, that gives us our total time. So we're going to do our vars, y vars thing. y1 plus vars, y vars, y2 and we're going to turn off the other two functions and just look at the total. Now, honestly, I have no idea where this is going to look like it's going. Oh, well, that's pretty cool. It looks like there's a minimum distance right around here at 1 to... Actually, I did have an idea. Because take a look at this. What's the most that x could be? X has to be less than 3, but greater than 0. So that'll be our x window. Let's go ahead and use that information. So for x, we're going from 0 all the way up to 3. For the y value, we're definitely going to be at 0 for the bottom. We're going to probably be more than that. And it looked like 10 was pretty good. Let's see what we have now. So it looks like we hit a minimum right about here. So let's calculate that minimum. Second, calculate the minimum. So we're going to press 3. Left bound, how about 0? Right bound, how about 2? Guess? It looks like it's probably about 0.5. And it looks like it is 0.5773. So if I were to kind of make this a little bit smaller here so we can see it, looks like x is going to equal 0.5773. Now there's a lot of advanced algebra in this that you could use to find that. And it says 0.5773 miles, I guess you could say. You could do this by hand. We could. But in the interest of time's sake and just the algebra part, I really wanted to focus on setting it up. So let's go ahead and finish the last two here. All right. So remember that idea of symmetry that we were talking about? It's going to come into play here. Definitely. It comes into play in all of them, but here you'll actually notice it quite a bit. So if we put a rectangle inside a circle, and the diagonal of this rectangle, keep in mind, we have x's and y's here, we got right angles. This is a rectangle. We could find this diagonal piece, because this diagonal piece is x squared plus y squared, and then square rooted. So what we're trying to do when we're looking at this question is says find the dimensions of the largest rectangle which can be inscribed into a circle of radius 4 inches. So it's the largest area rectangle, which is probably going to be a square. Probably. Let's see if we can figure this out. We know that the area of the rectangle is x times y. We also know that x squared plus y squared equals 8 squared. That being said, and notice here there's a constant in our secondary equation. That's kind of a clue too. The constant tends to go over there and all variables tend to go over here. We want to find a prime, but we got too many variables. So let's reduce some of it. Let's take out the x squared, for example. Or not take it out. Take out the y squared. So y squared equals 8 squared, or 64. Let's go ahead and take that back and write it 64. 64 minus x squared. And we got to square root both sides. So y equals square root 64 minus x squared. So this here is really x times square root 64 minus x squared. I'm going to show you guys a little bit of an algebra trick. It's easy to put two square roots together. It's not easy to put a non-square root and a square root together. So why don't I make this first term square root of x squared? That means that I can change this to square root. Now I got all one thing, 64x squared minus x to the 4. which even more simply is 64x squared minus x to the fourth all to the 1/2 power. That is going to be much easier to deal with in a derivative. So we're going to use some chain rule. We drop that 1/2 out front. It's going to be to the negative 1/2. Then we take the inside, just rewrite it. We've got to multiply by the derivative of the inside, which in this case would be 128x minus 4x cubed. Now if I were to clean this up a little bit, we're going to have a fraction with the top and the bottom. We have 2 times the square root of 64x squared minus x to the fourth. And on top we're going to have 128 minus 4x cubed. If I want to set that equal to 0, that's a prime by the way. If I want to set that equal to 0, then all I really need is the numerator. So let's set that piece equal to 0. 128 minus 4x cubed equals 0. If I were to do some algebra, 128 equals 4x cubed, if I move this over here. Divide both sides by 4. That gives me 32 equals x cubed. Go ahead and do the third root, or 32 to the 1/3 power, so 32 to the 1/3 power equals x. So what would y equal? That's kind of interesting. Is that right? What's going on there? Something seems a little bit off. Oh, this was an x. I know what we need to change. I forgot that x next to 128. So this is really 128x equals 4x cubed. So we're going to divide by 4 and an x. That gives me 32 equals x squared. Square root it, square root it. Square root of 32 equals x. Well, I know that y equals 64 minus x squared if I have y squared. So then 64 minus square root of 32 squared is y squared. So then 64 minus 32 is y squared. Y equals, or y squared equals 32. So y equals square root of 32 as well. So excellent, we got symmetry. X and y, same value, square root of 32. How would this change if the radius were r inches? Well, we can probably assume that it's going to be a, I can't even think right now. It's going to be symmetrical, so we're going to have a square. And if this is my diameter, then that means that this piece here is r over 2. And this piece here is r over 2. Notice that that was an 8 and became 64. So this is like our r squared. And that our answer was half of that. So it looks like if we take r squared over 2, and then we square root it, that's what our x and our y are going to be equal to. Now you could figure that out based on just working the problem out and doing the algebra, kind of working your way backwards. But using some intuition, you kind of shortcut a lot of this material. Okay, for this last one, I'm going to leave this for a tutoring problem. Go ahead and watch the videos as much as you can, but if you're still getting stuck on this one, we're going to cut it here because I got to get going myself. But it does a lot of the same things before. You're given the secondary equation, you're given the primary equation, you're going to make a substitution and make the calculation so that you can, looks like, minimize this piece here. Alright, have a good day.